Hey everybody, Mr. Piercy here, and what we're going to be looking at today is something known as the converse of the Pythagorean theorem. So the Pythagorean theorem, again, is a very popular math equation that says if I have two sides of a right triangle and I square them and I add them together and they equal to the third side of the triangle squared, a squared plus b squared equals c squared, well then the triangle must be a right triangle, and that's exactly what you're seeing on this first screen. Uh, Now, the converse of the Pythagorean theorem is a way that we can use the Pythagorean theorem to show whether a triangle is not necessarily right, but whether it would be an acute triangle or an obtuse triangle. Now, I did make a demonstration showing where the Pythagorean converse came from, and I'll put the link to that video in the descriptions for this one if you want to go back and check that one out. But let's go ahead and kind of see what we're going to be looking at here. Well, first of all, we want to be able to show, can we justify whether a triangle is a right triangle or not? Now, in the previous lessons, we've talked about Pythagorean triples, where all three sides of a right triangle were whole numbers. So if those work out, then we definitely have a right triangle. But there's a whole lot of other right triangles that can be formed where the sides are not whole numbers. So here's an example in A and B where if A is a right triangle, well, it means that the hypotenuse is not a whole number, so it's not a Pythagorean triple. And if B is a right triangle, because it has three whole numbers, it must follow the rules of a Pythagorean triple. Now, again, you may want to have just a couple of the basic Pythagorean triples memorized, particularly the 3, 4, 5 right triangle and its multiples. The next most common one would be the 5, 12, 13 triangle and its multiples. But here in these examples, what we're trying to do is, well, is the triangle a right triangle or not? Now, looking at the figures, you might say, well, it looks like a right triangle, so it must be a right triangle. And that would be an absolutely false presumption. You cannot do that in geometry. If you are going to say something is or is not whatever, you have to be able to justify it in some way. You can't say it is a right triangle because it looks that way. So taking these values here, what I'm going to look at is, again, I kind of look at the shorter side as A, the longer leg as B, and the longest side always has to be C. So that's kind of how, oops, A and B and C. So that's how I'm going to kind of substitute these things into the Pythagorean theorem. So looking here, they have it kind of set up in a slightly backwards fashion. I mean, it's not wrong. It's just normally we say a squared plus b squared equals c squared, but you can absolutely say c squared first. So taking those into account, I'm going to substitute the values into the problem. Now, pay attention, because the third side of the triangle, the longest side of triangle A, if it's a hypotenuse, we put that in for C. But because it's a radical value, pay attention that you're putting the entire radical value in parentheses, and then you're putting your exponent of 2. Then you're squaring it. Make sure you type it into your calculator that way. Now, at this point right here, what's really happening to tie in an algebra concept, this is property. This is a property of an exponent. What we would say here is basically we have a power of a power. Inside of the radical itself, or inside of the parentheses, I should say, the 3 and the radical 13, both of them would be considered a base. They're their own base that have an exponent of 1. And what I'm going to do is I'm going to raise the power to another power, meaning I'm going to raise the 3 that has a power of 1, and I'm going to raise that to a power of 2. So at this point, what we're really doing is we're kind of distributing the exponent on the outside to the exponents on the inside. So 3 squared gives me 9, and radical 13 squared is just 13. So that's how we're getting those two values there. That's the discrete operations that we're doing. Now you could just type in the parentheses radical 13 parentheses squared. You could type that into your calculator and hit enter, and it'll just give you your final answer. But I want to show you how the math is actually being taken place. So looking at the sum of the right side of the equation, 36 and 81, gives me 117. 3 radical 13 squared is 117. So the left side and the right side balanced. That means a squared plus b squared is in fact equal to c squared. So triangle A must be a right triangle. Doing the same process for triangle B, if I substitute the values here, I'm going to say 29 squared is equal to 16 squared plus 24 squared. But we're not really saying equal to. We have that little question mark over the equal to sign because we're not 100% sure. So squaring the left side and the right side gives us these values. And when I take the sum of the two values on the right side, we get 832. But if I square 29, I get 841. So in this case, because the left side and the right side are not the same value, we can conclude triangle B is not a right triangle. Now, on your assignments, on a quiz, on a test, this is the demonstration. This is the work I would expect you to show me. If you simply say, yes, it is, or no, it isn't, I'm not going to really give you full credit. You have to give me the math that justifies your statement. So please keep that in mind as you go forward. Now, moving on, now we're getting into the actual converse of the Pythagorean theorem. So at the beginning I said, well, not only can we use the Pythagorean theorem to show whether a triangle is a right triangle, like we saw in triangle A a second ago, but we can determine if a triangle is going to be acute or obtuse also by using it. So the difference here, and this is not something that is very easily remembered, this is something that a lot of students kind of struggle with sometimes. If c squared, that value, whatever it is, if it is less than a squared and b squared, the triangle will be acute. If, however, c squared is greater than a squared and b squared, then the triangle will be obtuse. And again, that's the purpose of the demonstration video that I made that I encourage you to watch to see, well, that's why it is. It's not just something that we're making up. There's a very good reason why. Now, both of these, even though they say 7.3 and 7.4, they're kind of written as two different theorems, they're really the same thing. This is the converse of the Pythagorean theorem. So the Pythagorean theorem can actually show us three things. It can show us whether a triangle is right, acute, or obtuse. So keep that in mind as we're going forward. This is a very common kind of SAT type question where they say, well, what type of triangle is this? And they give you three sides, and it may look like a right triangle, but you don't know. So here we have an example very similar to the kind of questions that you're going to see on your homework assignment. I don't know why the picture is, oh, there we go, that's why. There we go, get rid of the little dotted box there. Can the segments with lengths 2.8, 3.2, and 4.2, can they form a triangle? So there's actually two questions that were being asked here. So the first question that we're being asked is, can they actually form a triangle? So that's a yes or no question, and what that's doing is it's tying back to the triangle inequality theorem. Now remember, the triangle inequality theorem says if the sum of two sides is greater than the third side, then we will be able to form a triangle. But if the sum of two sides is not greater than the third side, we can't actually form a triangle. And at the time when when we went over that material, here you see in the handout and the notes that you see here, they have all three of these kind of here, where they're comparing all the different combinations of sides. And in my opinion, they're doing too much. If the two smaller sides are bigger than the third side when you add them together, then you don't need to worry about any other combination. So that's why I'm only really looking at the first combination. I'm going to take the two smaller numbers, add them together, and see, is it bigger than the third side? And since it is, the other two checks are not necessary. So I'm not going to worry about the other two. But you do need to recognize, keep in mind, can we form a triangle? And if not, well, we're not going to bother with the Pythagorean theorem. And since we're talking about the triangle inequality theorem, just as a quick reminder, remember, let me get rid of these little dots here. Not only does the triangle inequality theorem tell us if we can have a third, or if we can form a triangle by adding the two smaller sides and seeing if it's bigger than the third side, but it can also tell us the range of numbers of the third side. So here the third side has to be less than whatever two sides added together are, but it also has to be greater than two sides subtracted from each other. The sum and the difference, that's how we find the range of numbers that the third side of a triangle could be. So that's just a quick review of the triangle inequality theorem. So the first thing we would say is yes, these three side lengths can form a triangle. Okay, well, if we can form a triangle, what type of triangle is it? Is it right, acute, or obtuse? So since 4.2 is the biggest side, that's what I'm going to use as my possible hypotenuse. So I'm going to substitute 4.2 for C, and then I'm going to substitute the smaller side for A and the middle side for B. And using my calculator, I'm going to just take the square of both sides, okay, and add the two values on the right side, and we get 18.08. So what we're seeing here in this particular instance is that C squared is less than A squared plus B squared, which tells me, according to the triangle, or according to the converse of the Pythagorean theorem, that this particular triangle would be an acute triangle. Now, this is not my favorite example, but it is a really good practical thing that they could do. Now, again, just pretend that all of the solution stuff, just pretend that that's not there, and let's focus on what we're being asked. You're hoping to install a light pole in a parking lot, and what you want to know is it actually perpendicular to the ground? Is it actually going to be forming a right angle? Now, what we're doing here, let me go ahead and just try and draw this out a little bit bigger. Okay, so we have a light pole here, and I don't know, here's the light. And we want to know, is it in fact going to be perpendicular to the ground? So what they're doing is they're going to say, well, let's just use what we know about Pythagorean triples. We know 3, 4, and 5 will give us a right triangle. So what they're doing is they're kind of coming up, let me pick a different color here. They're coming up here 3 feet. And they're going to measure in one direction 4 feet. And so if they take their measuring sticks or their measuring tapes or something and they mark a spot that's 3 feet above the ground and a spot that's 4 feet away from the light post, if they measure the diagonal in between them and they see that that's 5 feet, well, we know that it's going to be perpendicular at that point. Okay? And what they're trying to show you in this last little diagram right here is that, well, we can't just do it from one point, and so they're trying to walk in a different direction. And I think it would have been easier to see, well, let's just say we're still coming up 3 feet here, and we're still going to come out 4 feet in the other direction, and if I measure again that diagonal, and I get another 5 feet, if we get that from two different positions, then we can reasonably say that the light pole would be perpendicular to the ground. Okay, so that's how they're kind of using that information just about right triangles in general as a real application. How would you know if something is going to be perpendicular to something else? So here's just a brief recap about the triangle, or about the Pythagorean theorem. A squared plus b squared equals c squared gives me a right triangle. If c squared is less than the other two sides squared, it's acute, and if it's greater than the other two sides, it's obtuse. So the last little bit here of your notes are just, a couple of questions for you guys. There's 4 questions here, and I want you to go ahead and we'll take a look at the first 2. Pause the video, work out these 2 examples, and see what you get as your answer. When you're done, hit play again and compare your answers with mine. All right, so hopefully we have some good answers here. Basically, what we want to know is, are these triangles a right triangle or not? Okay, so looking here, I have a shorter side here, A, a middling side here, and the longest side I'm looking here is C. So when I substitute my values in the Pythagorean theorem, I'm going to say that a squared plus b squared is 16, or I'm sorry, 4 squared plus 5 squared, and then 2 radical 10 squared, see what they give us. Well, we get 41 for the sum of the 2 legs, and 40 for what we think is the hypotenuse. So in this case, because the hypotenuse is less than the other 2 sides, or the longest side is less than the other 2 sides, I should say, this triangle is not a right triangle, it's actually an acute triangle. And repeating the same process on the other figure, here in this case, it is a right triangle because the 2 smaller sides, the sum of those two squared is equal to the third side squared. So again, one more time here, go ahead and pause the, take a look at these questions here. Again, question 3, there's 2 questions that are being asked. Make sure you answer both of them. And in problem number 4, it's kind of, in problem number 4, we're referring back to example 3. But go ahead and use the values that are provided for you. Answer these 2 questions, pause the video and answer them. And when you're done, come back and see what I got. All right, so first of all, can the triangles with lengths of 6.1, 9.4, and 11.3 form a triangle? So again, that's referring back to the triangle inequality theorem. So I'm going to look at those and I'm going to say yes, the 2 smaller sides added together is bigger than the third side, so these 3 lengths can indeed form a triangle. Was it right, acute, or obtuse? So substituting the values into the Pythagorean theorem, I get c squared to be greater than a squared and b squared added together. So that means this particular triangle is obtuse. And this is just a little typo. Those should be squares, b squared, c squared, and a squared, not a2, b2, and c2. But anyway. Now let's take a look at the last one. In example 3, could you use triangles with 50, 120, and 130 inches to verify that you have perpendicular lines? Now the key thing here is, did you explain your answer well? Well, taking a look here, I'm going to, now me, with all the right triangles I've seen, I know that 5, 12, 13 is a Pythagorean triple, so 50, 120, and 130 is just a multiple of the Pythagorean triple. But if I didn't realize that, I would just go to the Pythagorean theorem and see, well, is it a right triangle or not? In this case, a squared plus b squared is equal to c squared. So how do I know I have perpendicular lines? So here's my explanation. Since the sides of the triangle satisfy the Pythagorean theorem, it must be a right triangle. Therefore, the 50-inch segment and the 120-inch segment must be the legs and are therefore perpendicular to each other. So that's pretty much it for this video. All we're talking about again is the converse of the Pythagorean theorem, meaning that we can use the Pythagorean theorem to show if something is going to be a right triangle, an acute triangle, or an obtuse triangle based off of, substituting values into the Pythagorean theorem and seeing if c squared is actually equal to, less than, or greater than the sum of the other 2 sides. Let me know if you have any questions, ladies and gentlemen, and I'll be happy to answer whatever you might have. But until next time, guys, thanks for watching. Take care and be good.